Welcome back to my class in Abstract Algebra. Today we will take up subgroup, but before we formally define subgroup, we prove the cancellation law or cancellation property for group. We state the cancellation law for group. We let G be a group under the binary operation star. Because G is a group, we are sure that G is a non-empty set. That means G has at least one element. And because G is a group, under the binary operation star, every element in G has an inverse that is also in G. And also the identity element for the group is in G. We let A, B, C be any arbitrary elements of G. If A star B equals A star C, then B equals C. This is the cancellation law. It's like the element A was cancelled from the left and from the right. And we now prove this cancellation law for group. Again, we let A, B, C be any three arbitrary elements in G. And we would like to show that if A star B equals A star C, this implies that B equals C. Because A is an element of G, then A has an inverse. And we denote this inverse by A prime, such that if we combine A with A prime by the binary operation star, A star A prime is equal to E, the identity element in G. We write, since A is element of G, there exists A prime, called the inverse of A. Sometimes it is also denoted by A to the negative 1, but I will use A prime to denote the inverse of A. And the inverse of A denoted by A prime is also element of G, such that this is now the property of the inverse element of A. A star A prime is equal to A prime star A equals E, where E is the identity element of G. And the identity element has the property that if you combine the identity element E with any element of G under the operation by the binary operation star, the result is the element. And we multiply both sides of this equation by the inverse of A. And we use we multiply both sides of this equation by A prime from the left. That is, we write A prime to the left of A star B. If we combine A prime with A star B by the operation star, from the left we get A prime star quantity A star B. And we do the same for the right hand side to maintain the equality. We combine A star C with A prime by the binary operation star from the left, and we would get A prime Now, to this equation, we apply the associative property of a group. Associativity is one property that is satisfied by the elements of the group G. And by associative property, the left-hand side is equal to quantity A prime star A star B. We also apply the associative property to the right-hand side of this equation. By associative property, this is now equal to quantity A prime star A star C. Now we apply the property of inverse element of A, as we have written here, A star A prime, or the combination of A and its inverse A prime, which is equal to the combination of the inverse of A and A equals the identity element E. Hence, from this last equation, A prime star A is equal to E, the identity element of G. Also from the right, the combination of the inverse of A and A by the binary operation star, or A prime star A, is equal to the identity element E of G combined with C under the binary operation star. And by property of the identity element of G, if you combine the identity element E with any other element of G by the binary operation star, the result is the element. Hence, E star B is equal to B, and E star C is equal to C. Therefore, we have shown B equals E. And the end of proof is indicated by this small shaded rectangle. And that's the cancellation law for group. We now formally define subgroup. We now define subgroup of a given group. Let G be a group under the binary operation star, and we let H be a subset of G. Because H is a subset of G, every element of H is contained in G. That is, all the elements of H are also elements of G. But not all elements of G are necessarily elements of H. Then, we say H is a subgroup of G if the following conditions are satisfied. Number one, for every AB element of H, if you take any two arbitrary elements of H denoted by A and B, and you combine them by the binary operation star, A star B must be an element of H. And this first property of a subgroup is known as the closure property. That is, the subset H of G must be closed under the binary operation star. That means if you take any two elements of H as A and B and you combine them by the binary operation star, the combination of these two arbitrary elements must also be an element of H. And we say H is closed under the binary operation star. The second property is that E, the identity element of G, is an element of H. And the third property, if A for every A element of H, then A prime, the inverse of A, is also element of H. For H subset of G to be a subgroup of G, the identity element by this second property must also be an element of H. And by the third property, if H, a subset of G, is a subgroup of G, then every element of H, the inverse of every element of H, must be also in H, in the subset H. In the second property, we are not saying that there exists an identity element in H. We are sure that there is an identity element because G is a group, and one of the properties of a group is the existence of identity element. So we are sure that there is an identity element in group G, but for H to be a subgroup of G, this identity element E must be contained in H. And in the third property, we are not saying that the inverse element of each of the element of H must exist. We already know that every element of G has an inverse element that is also in G. And because H is a subset of G, every element of H, which is also an element of G, has an inverse. But by the third property, if H is a subgroup of G, the inverse element of every element of H must be in H. We are sure that every element of H has an inverse, but we want this inverse element to be also an element of H. We represent that in a diagram. In a group, we are given a non-empty set G under the binary defined under the binary operation star. And if G is a group, by the second property, the existence of identity element, the question we ask, is there an identity E in G? We want to make sure that an identity element exists and it is in G. While in a subgroup, we are given a group G under the binary operation star, and H, you can see, is represented by this small circle, and the small circle is inside the oblong representing the group G, and because H is a subset of G, every element of H is also contained in G. And the question we ask, And you can see E is in the oblong representing group G. That means G contains the identity element. And if you want to determine if H is a subgroup of G, the question to ask is the identity element contained in H? In a group, if you want to know if you want to determine if the given non-empty set G under the binary operation star is a group, the question to ask about the identity element is there an identity E in G? And when you ask this question, you are asking if there exists an identity element in G. In a subgroup, the question to ask if you want to determine if the given subset H of G is a subgroup of G, the question to ask is this question: is the identity element E contained in H? The identity element is in G, and we are sure G has an identity element E because G is a group, and we want to determine if H is a subgroup of G. And the question to ask is E, the identity element in G, also contained in H. We now take some examples of subgroups from abelian group and from non-abelian group. In our discussion of set, if A is a set, in sets, if A is a set, then A is a subset of itself, and we call A as a subset of itself as improper subset. And the empty set is, by definition, always a subset of every set. Thus, if A is any set, two subsets of A are A itself and the null set or empty set. And we have similar property in group and subgroup. If G is a group under the binary operation star, then G itself under the binary operation star is a subgroup of the group G. And the non-empty set containing only the identity element of G is also a subgroup of G under the binary operation star. And as we defined earlier, this subgroup containing only the identity element of G is called the trivial group under the binary operation star. And we write this as our first two examples of subgroups of G. For our first example, if G is a group under the binary operation star, then two subgroups of G are, first, the set containing only the identity element of G under the binary operation star is a subgroup of G. And this set containing only the identity element under the binary operation star is what we call the trivial group. in this example, it is referred to as a trivial subgroup of the group G. And the other subgroup of G is G itself. Under the binary operation star, G is a subgroup of G. Now we prove that the trivial subgroup consisting of the identity element E only under the binary operation star is a subgroup of G. And whenever you are asked to prove if a given non-empty set or subset of the group G under the binary operation star or under the given binary operation is a subgroup of G, you must verify the three properties of a subgroup. And the first property is the closure property. For any two elements of the subset of G combined by the binary operation must be also in the subset of G. And the second property of subgroup, the identity element is in the subset of G. And the third property, every element of the subset of G has an inverse, we are sure of that, but the inverse must also be in the subset of G. So I will prove that the trivial subgroup, the set containing only the identity element under the binary operation star is a subgroup of G. We would like to prove that the set consisting of the identity element E under the binary operation star of G is a subgroup of G. And the first property is the closure property. We take any two arbitrary elements of the subset of G. But in our example, this is a subset of the set containing the identity element E is a subset of G because the only element of this set E is an element of G. And we want to prove the closure property for this subset. Take any two arbitrary elements of the subset of G. But in our example, this subset has only one element. So we combine this element with itself by the binary operation star. And combining the identity element E with itself by the binary operation star, we have E star E is equal to E. And this the property of the identity element E. And we are sure that E star E is E because E is an element of G and G is a group and G has an identity element E with the property that if you combine E with any other element of G including E by the binary operation star, the result is the element. And here E is combined with the element E and the result is the element E. And the element E, the identity element, is an element of this subset containing the identity element E. That is, we have shown that this subset containing the identity element E of G is closed under the binary operation star. We have shown that this subset satisfies the closure property under the binary operation star. The second property, we verify that the identity element is in the subset. And the subset contains only one element and it is the identity element. So the second property is obviously satisfied. The third property, we showed that the inverse of E is also element of this subset containing the identity element E of G. Obviously, E is an element of this subset of G because this subset of G contains only one element and it is the identity element. And this subset, this set containing only the identity element is a subset of G. This implies that E element of this subset of G is also element of G. E element of G. And because E is an element of G and G is a group, E has an inverse. And the inverse of E is denoted by E prime. And the inverse E prime of E is also element of G. Because that is the second property of a group, the existence of inverse elements, and the inverse elements are also in the non-empty set G. And in G, the inverse of E is equal to itself. That is, E prime inverse of E is equal to E, the identity element, and E is an element of the subset, this subset containing the identity element. So we have shown the inverse E prime of E is contained in the subset containing the identity element, and the inverse of E is actually equal to E, which is exactly the element of this subset of G. Thus, we have shown the third property of a subgroup is satisfied. Therefore, we conclude that this subset containing the identity element E of G is a subgroup of G, and we indicate the end of proof by this small shaded rectangle. For our next example, we consider the set of real numbers under the binary operation addition. The set of real numbers under the binary operation addition is an example of a billion group, because we know from our algebra class that one of the properties of the set of real numbers is commutative property. And addition of real numbers satisfies the commutative property, that is, order in the sum is not important. So the set of real numbers under the binary operation addition is an abelian group. And the set of real numbers under the binary operation addition is a group because the set of real numbers satisfies the associative property for addition. And there exists an identity element in the set R, which is the zero, also known as the additive identity, with the property that if you add 0 to any other real number, the result is the real number. And the third property of a group, the existence of inverse elements. Every real number has an additive inverse, which is the negative of the real number, with the property that if you add the real number to its additive inverse, the result is the identity element 0, or the identity element 0. And because the set of real numbers satisfies the commutative property for addition, the set of real numbers under the operation addition is an abelian group. Now we write some of the subgroups of the group of real numbers under the binary operation addition. And one of these subgroups is the set of integers denoted by Z under the binary operation addition. The set of integers is a subset of the set of real numbers because every integer is a real number. And under the binary operation addition, the set of integers is a subgroup of the set of real numbers. Because if you add two integers by the operation addition, the sum is again an integer. And the identity element of the set of real numbers under addition, which is 0, is also contained in the set of integers. 0 is an integer. And the inverse elements of the set Z must be contained in Z, and the inverse of every integer is its negative. and the negative of every integer is again an integer, and so is contained in the set Z. Therefore, the set of integers contains three subsets: the set of negative integers, the zero integer, and the set of positive integers or counting numbers. Under the binary operation, addition is a subgroup of the set of real numbers under the binary operation, addition. Another subgroup of the set of real numbers under addition is the set of rational numbers under the binary operation, addition. The set of rational numbers under the binary operation addition is another subgroup of the set of real numbers under the binary operation addition. And a rational number is a real number that can be expressed or that can be written as a ratio of two integers. And if you take any two rational numbers and you add them by the binary operation, you combine them by the binary operation addition, the sum is again a rational number. Therefore, the set of rational numbers is closed under the binary operation addition. And the identity element 0, the additive identity element 0 of the set of real numbers is a rational number because 0 can be expressed as a ratio of two integers in many ways. Example, 0 is equal to 0 over 10. So we have written 0 as the ratio of the 0 integer and the positive integer 10. And so the ratio of 0 over 10 is equal to 0 and must be contained in the set of rational numbers. And the additive inverse of every rational number, which is equal to its negative, is again a rational number, only with opposite sign. And so we have shown that the three properties of a subgroup are satisfied by the set of rational numbers under the binary operation star. The set of integers under the binary operation star is a subgroup of the set of real numbers under the binary operation addition. The set of integers under addition is a subgroup of the set of real numbers under addition. And the set of integers under addition is a group. If it's a subgroup, then it is a group. And one of the subgroups of the set of integers under addition is the set of NZ under addition. The elements of NZ are multiples of the integer n. And the elements of NZ are obtained by multiplying every element of the set of integers z by the integer n. The set of integers is an infinite set consisting of the negative integers, the zero integer, and the positive integers. And the elements of and z are obtained by multiplying each element of z by the integer n. Example, 2z, the elements of 2z are obtained by multiplying each element of z by the integer 2. And so the elements of 2z are negative 6 multiply negative 3 by 2, negative 2 by 2, negative 4, negative 1 by 2, negative 2. 0 by 2, 0, 1 multiplied by 2 is 2, 2 multiplied by 2 is 4, and 3 multiplied by 2 is 6. And you can see the elements of 2z are integers that are multiple of 2 or divisible by 2, that is exactly divisible by 2. And this set 2z under addition is a subgroup of the set of integers under addition. Example, we verify the three properties of a subgroup. If you add any two elements of 2z, the sum is also in 2z. Example, negative 4 plus 2 is negative 2, and negative 2 is also in 2z. So the set 2z is closed under addition. The second property of a subgroup, the identity element of z, which is 0, must also be in 2z. And 0 is contained, you can see 0 is contained in 2z. And the third property of a subgroup, every element of 2z has an inverse, and the inverse is also in 2z. Example, negative 6. The additive inverse, the inverse of negative 6 under addition, we call it additive inverse, is positive 6. And positive 6 is also in 2z. If we take 2, the additive inverse or the inverse of 2 under addition is negative 2. And negative 2 is also contained in 2z. Thus, the third property of a subgroup is also satisfied. And we have just shown that 2z with these elements that are multiple of 2 or numbers divisible by 2, exactly divisible by 2, under the binary operation addition is a subgroup of the set of integers under addition. Now, we will prove in general that NC under the binary operation addition is a subgroup. We now prove in general that the set NZ is a subgroup of the set of integers under the binary operation addition. And to prove that, we verify the three properties of a subgroup. The first property is the closure property. So to verify the closure property, we take any two elements of NC. We let A and B be any two arbitrary elements of the set NC, and we use the fact that the elements of NC are multiples of the integer n. That means every element of sense NC can be written as a product of the integer n and an integer element of C. Because the elements of the set NC are multiples of n, if A is element of NC, then A can be written as the product of the integer n and an integer x element of C. Similarly, because B is element of NC, B can be written as a product of the integer n and an integer y element of C. That is, B is exactly divisible by n. If you divide b by n, the result is y, an integer, with zero remainder. Similarly, A is element of NC. That means A is exactly divisible by N. If you divide A by N, the result is X, an integer with remainder 0. And X is element of C. Now we add A and B, and we show that the sum is also an element of NC. And we conclude that the closure property of a subgroup is satisfied. We now add, we get the sum of A plus B, but A is equal to NX plus B, but B is equal to NY. And we have a common factor in these two terms. Common factor is N. We factor out N. If we factor out N, we get N multiplied by quantity X plus Y. Now, X and Y are integers. So the sum X plus Y is also an integer. Because we know that the set of integers is closed under addition. That means if you add any two integers, X and Y, the sum is again an integer. And this sum, this integer X plus Y, this integer, which is the sum of the integers X and Y, multiplied by N, must be an element of NC. Because we have shown that this is a product of the integer N and an integer element of Z. But this N times quantity X plus Y is equal to A plus B. And we have just shown that A plus B is element of NC. That is, if you take any two arbitrary elements A and B of NC, the sum A plus B, which can be written as the product of the integer N and an integer element of C, is also element of NC. Thus, we conclude that NC is closed under addition. The second property of a subgroup is that the identity element of the group must be in the subset of the group. That means the identity element for the group of integers under addition is 0. And we must show that 0 is also contained in NC. And we can readily show that 0 is an element of the set NC because 0 can be written as the product of an integer n and 0. If you multiply any integer n by 0, the product is 0. But here we have just shown that 0 can be written as a product of the integer n and the integer 0. Therefore, 0 is element of NC because it is a product of n and integer 0. That means if you divide 0 by this integer n, the result is 0, which is an integer, and the remainder is 0. Therefore, we conclude that the identity element 0 for addition is also contained in NC. In the second property of a subgroup, we thus conclude that the identity element 0 of the set of integers is in NC. And lastly, we verify that every element of NC has an inverse, and the inverse is again in NC. We let C be any arbitrary element of NC, and we know that NC is a subset of the set of integers. That is, every element of NC is an element of C. And we know that C under addition is a group, thus every element of C has an inverse. Particularly, every element of C has an additive inverse. The inverse of every element of C under addition is called additive inverse. So if C is element of NC and NC is a subset of C, then C is an element of C. Because C is element of C and C is a group under addition, every element of C, any arbitrary element C of C has an inverse denoted by C prime, and the inverse of every element of C is denoted by minus C. And we call this minus C the additive inverse of C. And the additive inverse of C denoted by C prime, which is actually equal to minus C, is also element of C. But initially we begin with C element of NC, and every element of NC can be written as a product of N and some integer element of C. So if C is element of NC, we can write C as N multiplied by some integer element of C. And we write but we now write C as the product of N and the integer U. That is C, because C is element of NC, C is exactly divisible by N. If you divide C by N, the result is an integer, U element of C, with remainder 0. And so this C prime equals minus C. C now can be replaced with NU. Now, using the fact that C is equal to N multiplied by U, the inverse of C denoted by A prime equals to minus C can now be written as, we replace C by NU, minus C equals minus, this is actually minus 1 times quantity NU, and we apply the associative property. By associative property, negative of quantity NU is equal to negative 1 multiplied by N, quantity negative 1 multiplied by N times U. And by commutative property, negative 1 times N equals N times negative 1. And to this one, we apply again the associative property. By associative property, quantity N times negative 1 times U is equal to N. Now we group negative 1 multiplied by U. But negative 1 multiplied by U is equal to negative U. Therefore, we have shown that negative C is equal to N times negative U. And this tells us that negative C, which is the inverse of C, is also a number of the form N multiplied by negative U, where U is an integer Z, therefore minus U is also an element of Z because C is a group and C contains its additive, its inverse elements, the inverse of its elements. So if U is element of C, minus U here is element of C. And we have shown that minus C can be written as a multiple of the integer minus U, element of C. That is minus C, the inverse of C, C prime, is equal to the integer N multiplied by the integer minus U element of C. Therefore, we have shown that every element C of NC has an inverse denoted by C prime and is equal to minus C. And the inverse minus C is, which is equal to this, is element of NC. Therefore, the third property of a subgroup is satisfied by the set NC. And for the third property, we conclude that NC contains the inverses of its elements. And because the three properties of a subgroup are satisfied by the elements of NC, we conclude that NC under addition is a subgroup of the set of integers under addition. We conclude that the set of integers NC under addition is a subgroup of the set of integers under addition. And we indicate the end of proof by the small shaded rectangle. We now show with an example that not every union of two groups or two subgroups is a group or another subgroup. We have just shown that in general the set NC, the set of integers that are multiple of n or exactly divisible by n under addition is a subgroup of the set of integers Z under addition. So consider the subgroup 2Z under addition and the subgroup 3Z under addition of the set of Z under addition, the set of integers Z under addition. Suppose we take the union of these two subsets 2Z and 3Z. To show that the union of the subsets 2Z and 3Z of the set of integers Z is not a subgroup under addition of the set of integers Z under addition, you only need to give one example that will not satisfy one of the properties of a subgroup. And if the union of 2Z and 3Z is a subgroup under addition, the definition of subgroup says that the closure property must be satisfied by the subset. And so if 2Z union 3Z is a subgroup of Z under addition, the closure property must be satisfied. Suppose we take 2, an element of 2Z. The elements of 2Z are those integers that are divisible, exactly divisible by 2. And the elements of 3Z are those integers that are exactly divisible by 3. And so the elements of the union of 2Z and 3Z are integers that are either divisible by 3 or divisible by 2. Now if we take 2, the element of 2Z, and 3, the element of 3Z, let us add these two integers. Because if there is a subgroup under addition, the closure property must be satisfied. That is, if you take any two elements of this 2Z union 3Z, the sum must also be in 2Z union 3Z. And we take 2 element of 2Z and 3 element of 3Z, and 2 and 3 are elements of 2Z union 3Z. Now we find the sum of 2 and 3. And as I said earlier, the elements of the union of 2Z and 3Z are those integers that are either divisible by 3 or divisible by 2. But the sum of 2 and 3 are elements of the union of 2Z and 3Z, but the sum 5 is not divisible by both 3 and 2. Therefore, 5 is not an element of the union of 2Z and 3Z. And this tells us that the closure property is not satisfied by the set 2Z union 3Z. And because the first property of a subgroup, the closure property, is not satisfied, we can confidently conclude that this set 2Z union 3Z under addition is not a subgroup of Z. And this is what I was trying to tell you, that if you have two subgroups of a group and you take the union of these two subgroups, the union may or may not be a subgroup of the given group. And this is an example where we have 2z and 3z that are both subgroups of the set of integers c under addition, but their union is not a subgroup of the set of integers z under addition. Earlier, we have shown the trivial subgroup, the subgroup whose set consists of only one element, the identity element of the non-empty set of the group under the binary operation star is a subgroup. The trivial group consisting of the set with only one element, the identity element we have shown, is a subgroup of the given group, of any group. Now, for your exercise, please try to prove that G itself is a subgroup of itself. Prove that G is a subgroup of G under the binary operation star. And that completes our lesson for today. And if you have questions about the lesson today, please ask your questions in the comments below. And we will have more examples of subgroups in the next lesson. Thank you for joining me in my class today in Abstract Algebra.